So what we have seen so far are just two examples, the Malthus model and its extension, the Malthus model with logistic. So what was peculiar about these two examples is that they had no input u. So we had our output. I implicitly assumed that our output was the population size, because that was the only actually possible quantity that we could choose, but they had no input u. So they were isolated systems. Now we are going to consider a situation where we are going to have an input u. So as a special case that we are going to consider is a class of models that we call first order models. So we say that a model is a first order model or system if we can write a state representation for it where the state x is a scalar. Okay, so for example, x dot equal to f t x and u, with x a real number, is a generic expression for first order model. A particularly interesting case, so an interesting case, is when the function f of t, x and u does not depend on t and it is linear. In this case we say that it is a linear time independent or time invariant system. So first order linear time invariant system has the form x dot equal to, there is no dependence of time, this function has to be linear in x and u, so can be written as ax plus bu. Okay, and for simplicity assume also u as a real number, even though this is not really necessary, but we have this assumption here, and of course since it's a first order we have to specify that x is a scalar. Of course we can put our initial condition, x at time 0 is going to be given by a certain quantity that we know, and of course this quantity has to be scalar because the system is a first order system. notice the difference now compared to what we had before. The main difference is that we have a term bu, so we have an input. Let's try to see if we can solve this differential equation, because we are having a differential equation that is similar to the other differential equations that you might have seen before. The only difference is that this quantity u of t is a quantity that depends on time, and it's not a priori specified. So the system is definitely not isolated. Let's see what is the shape that the solution of this differential equation gets under the assumption that actually we can solve the system. So in order to find the solution to this differential equation, we apply a change of coordinates. We apply the following change of coordinates. That is going to make everything simpler. We define z of t. By definition, when I use this symbol instead of equal, I mean that I'm defining this quantity, and I define z of t as exponential of minus at x of t. So this is a change of coordinates that changes with time. So I want to compute z dot. Z dot is the time derivative of a product, so I have to differentiate the first part. The derivative of exponential of minus at is given by minus a exponential of minus at times the second factor left unchanged plus the first factor unchanged that multiplies the derivative x dot. The nice thing is that now I have minus a exponential of minus at x. I'm omitting the argument of t plus, and now I can replace x dot with the expression that is given to me by the dynamic state equation. So I have exponential of minus at that multiplies ax plus bu. Okay, as another step, we do the following. We have minus a exponential of minus atx plus a exponential of minus atx plus exponential of minus at bu. As you can notice, these first two terms cancel each other out, giving us a simpler expression that is z dot equal to exponential of minus at bu. Okay, this is very easy to solve, because if I integrate this from 0 to t, I obtain that z at time t minus z at time 0. Remember, I'm integrating z dot, the derivative of z with respect to t, so when I integrate it, I get z itself. This needs to be equal to the integral from 0 to t of the exponential of minus a tau b u of tau in d tau. I'm using a different variable inside the integral. I don't want to have a t here if I'm using t as an extreme of the integral. Okay, so now I found z of t, because z of t is equal to the initial condition for z plus this integral that is exponential of minus a tau b u of tau in d tau. The only thing I'm left with is now to go back and find out my change of coordinates, that is this one here, and there is an observation. When t is equal to 0, z0 is equal to x0. So this implies that now I replace z of t with its expression, that is exponential of minus at x of t, So exponential of minus at x of t needs to be equal to exponential of minus a times 0, x of 0, but the exponential of 0 is 0, so this is just x0, plus the integral that we had before. And we are left only with the final step to find the solution of this equation, because now we multiply the left-hand side and the right-hand side by exponential of at, and we get that x of t is given by the exponential of at x0 plus the integral from 0 to t of the exponential of a t minus tau b u of tau in d tau. So this is what the expression looks like for the solution x of t. A couple of observations here. The first term, so this formula is called variation of constants formula. Remember this because, as a side note that I'm putting here, this is going to work also for systems of higher order. So we are just seeing in a very specialized way something that we'll see it's way more general. So the comments that I start making now, even though they apply to this specific case, they're going to be applicable also to systems of a more generic form, so long as they are linear. The main thing that we have, the main property that we have used to obtain this formula is the linearity. So the first comment that I want to say is that the exponential of at x0 is called free response. And the reason is quite simple. It doesn't depend on u. When u is equal to 0, your input is 0, so you're putting no input into your system. The only c that you see, at least in your state, is going to be given by the initial condition. So that's why it's free response. This is how the system would respond freely with no input. And instead, the other term that has this form, exponential of at minus tau b u of tau in d tau, is called a forced response. It is the response that you would have if you had no initial condition, so x0 equal to 0, so the free response would be 0. Then in that case you would only have this integral, and this integral is given by depends on your u of tau. So this is the part of the response that your system gives you when you're injecting a certain input u of tau. This integral here has a special form. Remember, this form is called convolution integral. Convolution integral. And you can also write this in this way: exponential of a tau convolution b u of tau. It has this form here. We are going to see these things a little more in detail, of course, once we introduce the Laplace transform. The Laplace transform will give us this convolution formula in a sort of natural way, this convolution integral, convolution product. And we'll see this in a little more detail when we see higher order systems. But it's good that you start seeing these things in simpler cases, so that it's going to be easier for you to generalize later on.